I'd just like to say welcome to HAAS members and also to visitors from our North of Scotland sister astronomy clubs, Aberdeen Astronomical Society, Caithness Astronomy Group, Murray's Astronomy Club Sigma, and North Ronaldsay Astronomy Group. I'm not sure if there are visitors here who are not affiliated to any of the clubs, but if you are here, then you are most welcome. So tonight's timings, I'm going to do this very brief welcome and notices, and then we'll follow that with the main talk from Neville Brown, followed by Q&As, which will be moderated by Paul. At round about 8:30, we will have club news, astro picks and targets for the month. Pauline will be doing that. And about 8:45, 8:50, we'll do a little session, club member Q&As, and that will take us to the meeting close. Just to note, there won't be any breaks during the meeting. So if you need a cup of tea or a comfort break, just get up and go and keep yourself connected to the meeting so you don't have to go through the palaver of reconnecting when you rejoin. Now, at the March meeting, we mentioned that we were going to be holding our AGM in April. Well, as you well know, we were unable to hold our AGM in the flesh this year. However, Oscar, the Scottish Charities Regulator, they encouraged organisations to be creative and formally demonstrate that they comply with charity law and that they report their annual accounts. We are pleased to say that we have achieved both key requirements, and I wish to thank all the club members who acknowledged the AGM email sent out by Rona, the people who contributed to and approved our club's annual report and the accounts, and they'll be submitted to Oscar in due course. As you read, our existing office bearers will remain in position, and I am now the official chairman of Highlands Astronomical Society. So, Paul, the clock starts now, according to yourself. Our treasurer, Andy Brough, compiled a robust operating plan, and we are in an acceptable financial position. That is provided members are willing to pay their annual subscriptions, which our membership secretary, Gail Hilliard, has and will be chasing up over the next month or so. So if you could do the necessary and rejoin and pay your subs, that will be a great help to us all. Now, regarding keeping in touch, we hope that all our members have been enjoying the email, the Facebook and Instagram links to various astronomy-related articles and events over the past couple of months. Pauline has been very diligent in emailing these, along with some astro picks. And also, there was a great astronomy crossword, which I nearly managed that was sent out last week. We're also considering running a club hub. That could be something as simple as a wee get-together every so often for like-minded club members to chew the fat, shoot the breeze, using Zoom meeting. I'm sure many of yourselves, your children, grandchildren will already be doing this regularly and keeping in touch with all their friends. Regarding the observatory, well, we've been unable to use our observatory since the lockdown. However, there's a small group of us working on ways to use Zoom to have live observing sessions and teaching or tutorial sessions from our own home observatories, which members can participate in. So just watch this space. For your diaries, our next meeting is on Tuesday, the 7th of July, and it will also be hosted via Zoom webinar. We're pleased to let you know that our next 3 speakers have all confirmed that they are happy to talk using Zoom webinar. So that'll take us through to September, when hopefully circumstances may have changed a bit. Anyway, that's enough for me. I'm now going to introduce our main speaker for tonight, Neville Brown. Neville Brown is retired, meaning he can now do all the things that he wants to do. He had a dual career, first as an engineering manager with a major oil company, and secondly at Robert Gordon University. Neville's a keen astronomer and has been so for many years. He's interested in both practical observing and also learning about the subject and science of astronomy itself. He's a committee member at Aberdeen Astronomical Society, and he organises and promotes their astronomy outreach education programme. Neville himself gives talks to schools and various organisations such as Scouts, Guides, walking troops, and of course other astronomy clubs. His lecture topics cover subjects such as distances in space, age of stars, what to see in the night sky, simple guide to astro equipment and how to use it, and various aspects of the history of astronomy. It's with great pleasure that I welcome Neville tonight, and here he is to talk about the rise of astrophysics, 1890 to 1930, a story of 4 remarkable women. Over to you, Neville.
Thank you very much, Eric. Quite a build-up. Hope I can live up to it. Okay, I'm just going to start sharing my screen. Hopefully that will come up just fine. So I'll just put that onto, there we go. I'm just going to bring the pointer up and put that in the corner. Great. Right. Thank you very much. Okay. So welcome everybody. Yes, the talk is the rise of astrophysics 1890 to 1930, and as you'll see, that was a period when there were some remarkable advances made, and in some ways one could argue that that's where the term astrophysics was probably born. By astrophysics we mean why are things the way they are, as opposed to there's a star, there's another star, there's a nebula, there's a galaxy, etc. So it's really, so why is that star different to that star? And that's really the key to this whole story. So we start with this remarkable picture, which was taken in 1918 in front of one of the buildings at the Harvard College Observatory in Cambridge, Massachusetts, just outside Boston. And I will introduce you to some of the women in this picture, but the most remarkable thing you probably see straight away is that it's virtually all women. Okay, and these women are all astronomers. They're all professional astronomers. The 2 blokes at the end operate the telescopes. The women weren't allowed to operate the telescopes, but they are bona fide astronomers. And this is 1918, so there's a clue straight away. Obviously, this was a bit different here. Okay, so let me move on to introduce who the players are going to be. Well, we're only going to talk about 4 of these, the women that basically were these group of female astronomers at the Harvard College Observatory. The first one will be the lady top left, Mina or Wilhelmina Fleming. We'll then talk about Annie Cannon. We'll then go out of sequence and talk about Cecilia Payne, or Cecilia Payne-Gaposchkin, as she became known after she married one of her students, Sergei Gaposchkin. And then we'll go back in time again to Annie Cannon's time to meet the 4th lady, Henrietta Swan-Leavitt. And there's a reason for going in that order, and you'll see why that is in due course. So let's explain a little bit about where we are. Well, we're at the Harvard College Observatory, right next to Harvard University, or Harvard College as it was at this time. And here we can see a picture top left of the observatory as it was in 1899, around about 1899. And you can see that it's clearly kitted out for observing the night sky, and indeed not just observing it, but taking photographs of it. And remember, we're still fairly early here in the era of being able to take photographs of the night sky. Photography essentially having been invented around about 1840, I guess, roughly. So our sort of starting point is the Harvard College Observatory, but we need to introduce the person who's going to kick this off, because without him there would be no story, and that is Henry Draper, the guy you see with the fabulous beard bottom right there. So Henry Draper was a doctor and a lecturer in medicine at a university in New York. But he was mainly a fanatical astrophotographer. And you can see when he was young, that wasn't too many years into the birth of photography at all. So he was right in there at the start of photography and actually taking, photographs of the night sky. And indeed, he's the first person to record the spectrum of another star on a photographic plate, which he did in 1872. Now, that would more or less be the end of our story, if it weren't for the fact that you can probably tell by the dates there, 1837 to 1882. Henry unfortunately didn't live very long. When he was 45, he caught a chill while observing one evening. It turned into pneumonia and he died a few days later. Of course, these were very different times, of course. Now, you know, what we have to understand at this time is that he was very advanced for what he was doing. He was one of the very few people in the world that was looking at star spectra on photographic glass plates and thinking there's something different about this star and it's different to that star, etc., etc. This was a whole new science at this point. And his wife, who we'll meet here, Anna Palmer Draper, this was a picture painted a few years after Henry passed away. And you can see she was a New York heiress. She was extremely wealthy. The Palmer family had made their money from railroads and real estate. And you can imagine at that time, that means you make a lot of money, a lot of money. So she was a very, very wealthy woman. And in fact, she persuaded Henry that he should give up being a doctor and sort of concentrate 100% on astronomy and astrophysics. So she's really responsible for sort of promoting him in what he was doing. But after he passed away, she wanted to sort of keep his work going. She was very well aware of the work that he was doing because she would have been taking a lot of the notes while he was observing. So she was, although she didn't know a lot about astronomy, she knew enough to be able to make sure she was making logical notes, etc. So what did she do? Well, initially she thought she could probably carry on his legacy and the work he'd been doing by sort of hiring someone in to do it. But it soon became apparent that that wasn't going to work. And what she really needed to do was to latch onto a much bigger organization, which she did by latching onto the Harvard College Observatory and agreeing to start to bequeath money, initially about $200 a month, eventually something like $400,000 in total. That's an enormous amount of money in that time. And it's basically to fund what became known as the Henry Draper Memorial Project. And what is that? Well, simply put, it's basically photographing the spectra of stars and star fields on these glass plates, these 8x10 and 10x14 glass plates, in order to classify stars. So this is purely what the Henry Draper Memorial Project is. For the first time ever, it's trying to classify stars. Why is star A different to star B, etc., etc. So who was the director of the Harvard College Observatory? Well, that would be Edward Pickering. He'd been a professor of physics at the then Massachusetts Institute of Technology and was lured away from there to become the fourth director of the Harvard College Observatory, where he stayed until he passed away in around about 1920. He was also a key pioneer of astrophotography and what it could do. And it's him that he is really responsible for what we'll call in a minute and learn about the computer team, as it became known. He was one of the most honored scientists of that period, was Edward. So what do we mean by computer? Well, obviously we don't mean a computer as we know it today. We mean people computing numbers. And the issue here was there were more and more sort of these photographic plates, initially from star fields and then from spectra, and we'll look at one of those in a minute to give you a sort of an idea of what we're talking about. So the number of plates was sort of building up initially from taking photographs at the Harvard College Observatory, but of course its proximity to Boston started to really knock that out in the early 20th century. And more and more they started taking photographs and spectra from California, and as we'll see in a minute, from South America, and we'll see that in just a minute. But the issue then was, well, it's okay to take these glass plates, but we really need to analyze what's on them. And that's where this computer team comes in. Okay. Now, once he started to get money flowing in from Anna Palmer Draper, who we just saw, she was donating money to the cause here. He needed to hire people to start to analyze the spectra of stars on these glass plates and start to get to grips with why is this one spectrum different from another. And remember, this is a time before quantum physics, before nuclear physics. We didn't know anything about the atom. Okay, so this is purely trying to grasp at why are stars different from other stars purely by what you see in their spectra. We didn't even understand why the sun shone, remember, until about the mid-1920s. So he realized he needed to sort of hire people, and he came up with the idea that he would try to hire women to do this work. He had contacts at the major women's colleges, Wellesley and Radcliffe and Vassar in New York, Wellesley and Radcliffe in Boston. And he talked to the people that ran those colleges, and he also put an advert in the local paper saying that he would really value these sort of educated young women at the time. Remember, they couldn't get jobs anywhere else at this time. Remember, you know, they would never use the education they got. These were very different times. Remember, and he was flooded with applications, and he picked the best 14 and employed them at the Harvard College Observatory. This would be about from 1880 onwards, just before 1880 onwards, to start to do this task of sifting through all this information. And we'll talk a lot more about that in a minute. Now, before we run away with the idea that Henry was fully enlightened for a man of this era, he was enlightened up to a point, but of course he wasn't daft either. He'd already realized that he could employ 2 women for what he could pay 1 man. So he was basically spinning his money out rather carefully here. So he was enlightened, but maybe not as enlightened as we might think. Okay. So here we've got a picture of the computer team circa 1911. So this is 7 years before the group that we were looking at when we first looked at that first picture. And I'll show you 2 of the women we're going to talk about in here. This lady here is Mina Fleming, and the lady here is Annie Cannon. Okay. The first one we're going to talk about is this lady here, Mina Fleming. But before we do that, we need to make a small diversion down to Peru, because thanks to Pickering, that's Edward Pickering, had always had the idea that what he really wanted to do was to have an observatory in the southern sky so that they could cover the whole of the southern sky and the northern sky. And as luck would have it, about $250,000 came his way, he had to fight for it, but it ultimately came his way in the will of an extremely eccentric inventor called Uriah Boyden. And shortly thereafter, there was also a donation by yet another New York heiress, Catherine Wolfe Bruce. And that money was more than enough to set up a southern observatory, which they did it would have been set up, I guess, around about 1890. It says there, opened in 1890. The first director was actually Edward Pickering's younger brother, William, who was also an astronomer, and it was named the Boyden Observatory, obviously after Uriah Boyden, and it actually stayed in Peru until the sort of the late 1920s, as you can see then, when it was relocated to South Africa, because the weather really wasn't that great actually in Arequipa. So here we can introduce the first of the 4 women we're going to talk about, Wilhelmina Fleming, or Mina Fleming as she was called. She was Scottish. She was from Dundee, in fact. She was a teacher from Dundee. She emigrated with her husband James to Boston, where she had 3 brothers already working in Boston or in the Boston area. But James Fleming, having discovered that his wife was pregnant, decided that he didn't want to hang around, and that was the last she saw of him, I think, ever. So she's been basically abandoned very quickly in Boston with no job. She's pregnant. Obviously, her brothers were there to support her. But as luck would have it, she she did manage to get a job working as Edward Pickering's housemaid. But of course, Edward Pickering, being the sort of guy we've just learned, we very quickly realized from his conversations with her that he was talking to someone here who should not be his housemaid. She should be working as a computer, basically in the observatory, and that's exactly what he did. She wasn't doing housework for very long. Pickering agreed that further on in her labour, he sent her back home to Dundee. She had the child and then came back a few months later to the Harvard College Observatory, or I guess it was about a year later actually, to the Harvard College Observatory, having left the child in the care of her grandparents. She was extremely grateful for Edward Pickering, for what he'd done. In these times, that was a remarkable thing for him to do. And in fact, she named her son Edward Charles Pickering Fleming. So basically, both of Pickering's first name and the word Pickering as a middle name. She was so grateful for what he had done, basically. Now, what did she do? Well, what Mina Fleming did initially was she worked as a computer, basically sort of getting to grips with looking at all these glass plate slides and trying to work out why is one star spectra different to another. And the only thing she had to go at was really the sort of the width of the lines in the spectrum, and we'll look at a typical spectrum in a minute, how dark they were, how light they were, how broad they were, etc., etc. There's no real physics in it. It's really just trying to grasp at anything you can. And she analyzed several thousand stars on her own. And then she became ultimately the supervisor of that group. And in 1899, she was actually promoted to an academic position as the curator of astronomical photographs, as the first woman to hold any significant position at Harvard, and one of the first in America in science, actually. The reason we remember Mina Fleming is she supervised the production of the first universal star classification system. It wasn't right. There were quite a few mistakes in it, but without what she did, then what comes next would not have been possible. So, and we'll talk about that a bit more when we talk about Annie Cannon. There's a typical light spectrum from a typical star. It's very much idealized. And this just gives you a bit of an indication of the kind of thing they would look at. They wouldn't look at anything like this, by the way. This is very much idealized. And you'll see in a minute there, what they were looking at is far more difficult to interpret than this. But the point I'm trying to make here is not the color, but these dark lines. And of course, what we now know is those dark lines are a consequence of subatomic particles moving around in energy levels within atoms. But of course, they didn't know that. All they knew is they're dark lines and they're relevant to the different elements that exist in the sun's atmosphere. So that bit they did know, but they didn't really know why. Okay. There's a typical glass plate photograph from the Harvard College Observatory from this era, and you can see there are two galaxies on there, several stars, and you can see sort of quite a lot of writing on it, which would be on the flip side, by the way. Basically the negative would be on the other side, and the writing would be on the flip side. They wouldn't be writing on the actual piece where the photographs taken, but that was quite normal. They often wrote, what they were doing on the slide. And there's a typical group of spectra on a photographic plate. That one actually, as it says there, is from the preset cluster. So basically, that's I guess that's M44. And basically now you can see what's going on here. So they've figured out a way of putting a big glass prism in front of the telescope tube and basically being able then to spread the light out from several different stars at once. So you're not seeing the stars as a dot anymore, you're seeing them as a drawn out line. And basically they would look at in great detail with a small eyepiece at the properties within each line, and from that try to understand why one star is different from another. So that's the kind of, shows you a bit about the kind of sort of level that they were working with here. But they would have been looking at hundreds and then thousands of these plates. This was a very laborious work. I should just mention briefly the other thing about Mina Fleming is that she really introduced the first Draper catalogue, I guess. Remember, Anna Palmer Draper was very insistent that the money she gave had to be used only for the Draper catalogue. So Annie Cannon, the second of the people we're going to talk about. Okay, so she comes really after Mina Fleming and worked for Mina Fleming when she first arrived in 1895. Initially unpaid, that was quite a few people wanted to come and work at the observatory. So Pickering didn't always have the money to do that. So, you know, they were quite happy to come along and sort of have a trial almost. But to his credit, he very quickly found the money once he realized that he had this on some very, very clever people who were able to do this work. And none more so than Annie Cannon. There's a picture there you see is her very much in later life. But she really is the sort of the one that really cracked the code, if you like. She worked all her life pretty much at the Harvard College Observatory working on star spectra. So she both did the work herself, and once Mina Fleming passed away, she basically took over as the supervisor, and things really went up into top gear. It's reckoned that Annie Cannon analysed something like 200,000 star spectra herself in her lifetime. And in fact, because things had become a little more enlightened by this time, she started to get sort of showered with honorary degrees and things like that, which were not things that were really given to Mina Fleming in those earlier days. What's interesting here, though, is well, her classification of stars, which we'll see in a minute, which was ultimately published in the Draper Catalogue in 1901, is actually the same system we still use today. So that it didn't really change. It was modified. People have added to it, but the basic system of star classification that we'll use today in any sort of astronomical dictionary or whatever, or any astronomy book, is the same one that she basically found out in 1901. She continued to analyze star spectra, and say, until she died at the age of 78. Now, what's fascinating about this is that you know, remember I mentioned that Mina Fleming was the curator of astronomical photographs at the Harvard College Observatory. Well, Edward Pickering sort of almost assumed that Annie Cannon, because she'd become so good at what she did, and she was known, she would have been known all around the world by all the main astronomers anywhere in the world as to who she was at this point. And he just thought it was a shoo-in, basically, that she would become the new curator of photographs. But the head of the board of Harvard College refused to do that. He was a guy called Abbott Lowell, and he was the younger brother of the famous Percival Lowell from the Flagstaff Observatory in Arizona, he of the canals of Mars. He thought he could see vegetation and people on Mars, or canals on Mars. But his brother was not very enlightened and said, no, we're not having another woman as the curator of photographs. And it wasn't actually until he retired that the governing board basically gave the job to Annie Cannon. And that was just 3 years before she passed away. So, you know, another interesting story there. She would have been well paid, though. I mean, she wouldn't have stayed that long if she wasn't, you know, making a reasonable living out of it. And she was very dedicated to it, along with Edward Pickering for most of that time. She was very much the sort of number two, if you like. And there we can see a picture of Annie Cannon and Henrietta Leavitt. They're at the front of one of the brick buildings at the Harvard College Observatory, which were built right at the end of the 19th century. The reason was because Edward Pickering thought, you know what, if we don't build brick buildings, we're going to have the same problem as what happened in other major city in America. They're going to burn down, basically, because all the buildings were made of wood. And he had all these thousands of glass plates, and that's why they built the brick building. And that's the star classification system we know today, of course. OBA, FGKM, basically, that's the main body of it. There are other bits at the top and bottom of that, but and it looks very simple when we see it now, because we can see the link with surface temperature of the star going down and the color. but the surface temperature versus the classification wasn't known to Mina Fleming, and it wasn't known for quite a lot of the time that Annie Cannon was working on this. So they were kind of feeling at this without the information that was needed to really get to grips with it. And we can see our sun there, as we know now, is a G-class star, yellow star, 5,600 degrees K. So it looks very simple when you see it now, but of course, Mina Fleming, by the way, had devised a system which went from A to O, A, B, C, D, E, F, G, K, right the way through to O. And you can see that what she got wrong was that the O class should be at the beginning, not at the end. And because she didn't understand the link with temperature, that's why that went wrong. But other than the A and B being in the different order, you can see everything else is still in the same order. But some of the letters were removed as being superfluous. So she didn't get it all wrong. She was very much on the right track. Okay, we need to skip on a bit now to Cecilia Payne. Now, this is a very different story because Cecilia Payne, to start with, was British. She was at Cambridge University in the UK. She was extremely bright. She came from an extremely bright family. And she was studying sciences, botany, physics, and chemistry. And she had the good fortune to go along and listen to a lecture one day by Sir Arthur Eddington, or he would have been Arthur Eddington, then he would have been knighted at that point, because probably one of the 2 or 3 most famous British astronomers of all time, Arthur Eddington, who was at Trinity College, Cambridge at the time, as a lecturer. And she was completely bowled over with this idea of working and having a life in astronomy. She thought this was for her, basically. And she then, that sort of got cemented just a year or so later when Eddington and 1 or 2 other people were going to London to hear Harlow Shapley, who had just taken over from Edward Pickering as the new director of the Harvard College Observatory. Remember, I mentioned Pickering passed away in, I think it was 1920. And Shapley was very much the rising star of astronomy in the US. And if she was bowled over by what Eddington said, she couldn't believe what Shapley was saying. She thought, oh, this is, I've got to do this. This is just, I've got to get over there and be a part of this. And Shapley very much encouraged that. She met him actually just after the talk. And she took him very seriously. Whether he was serious about her coming over or not, she was definitely serious herself. And that's why it says Cambridge to Cambridge at the top, Cambridge, UK to Cambridge, Massachusetts. And she went over there and she was given a job over there by Shapley. Initially started looking at star spectra, but he very quickly realized that she had far more skills than that. And he started looking at stellar composition to try and crack the issue of what is the sun actually made of. Obviously, they knew by now which elements the sun was made of. Yeah, that's fine, but how much of each? So how much of each element? Nobody knew that. And he also Shapley also encouraged her to study for a PhD at Harvard. So that was one of the first women to ever do that either. And Shapley being so famous, that would not have been blocked. And by this time, it probably wouldn't have been blocked anyway, to be honest, but just to make sure, with a guy like Harlow Shapley pushing it. Well, not only did she get her PhD, but her PhD basically is she worked out what the sun's actually made of. It's gone down in history as one of the most famous PhD theses ever by anybody. Basically, this is what she worked out by applying the new new work that was coming out of quantum physics at the time and new ideas about relating quantum physics to what you're actually seeing in the spectra of stars, basically, and the spectra of other elements. You were able to sort of work your way through to try and understand roughly how much of each was there. And that's what we know today. There's 70% hydrogen, 27 helium, and a few other bits and bobs, beryllium, lithium, boron, etc. That's basically what she worked out as a PhD thesis. And there's a picture of Harlow Shapley, the new director, and very much he was very much on Cecilia Payne's side. Unfortunately, one thing he got wrong, of course, as many people might know, he was a very strong supporter of the one galaxy hypothesis. He didn't believe there were other galaxies other than our galaxy. Well, he got that one wrong, unfortunately. Now then, Henry Norris Russell, right, he was the leading US astronomer of the day at Princeton University. And why have we introduced him? Well, basically because when Cecilia became sort of hot news that Cecilia Payne's PhD thesis was indicating what the sun was made of, several sort of leading astronomers, and Russell was one of them, thought, well, that's very interesting, but it can't possibly be true because we all know that the sun must be made of the same stuff as the Earth is made of. Why would it be anything different? And that was a commonly held belief. You know, if the Earth's made of silica and a few other bits and bobs, you know, then the sun must be as well. Remember, they had no idea why the sun shone at this point. And he kind of discouraged Cecilia Payne from publishing, actually. And in fact, she even put a footnote on her PhD thesis and subsequent writings saying, you know, it looks like this is right, but there's clearly something wrong with it because it can't really be true. And it was only several years later that Russell finally wrote a paper saying that actually she'd been right all along. Almost needless to say, he didn't actually write that in glowing letters, but he did acknowledge it, and he did acknowledge it to the world. So the other thing about Cecilia Payne that's interesting is that things had moved on a bit, and she really was well known and became very, very much one of the leading female astronomers in the world during her lifetime. But even for her, even though she was made a professor of sorts in 1938, when she was 38 years old, she didn't get full academic privilege of Harvard College until 1958. So she was 58 years old before somebody finally realized, okay, fair cop, we'll treat you as a full academic. So, you know, things were still not very enlightened even at that time. Okay, let's skip on to Henrietta Leavitt, the last of these four amazing women, and this one is my favorite. So Henrietta Leavitt joined the Harvard College Observatory the same year as Annie Cannon. They had something in common, actually. I should have mentioned this before. Annie Cannon was quite deaf, not completely deaf. She could use a hearing aid and could hear. A bit different for Henrietta Leavitt. She was very deaf. It was very, very difficult for her to hear very much at all. And that may have been one reason why she tended to be really quite introverted and really got on with the work herself. But she had a prodigious ability. Well, again, she started initially unpaid at the Harvard College Observatory, but Edward Pickering very quickly realized that she was very much a superstar in terms of what she could achieve. Initially, she did star spectra stuff like the rest, but then after she'd been there 2 years, she went back home to Wisconsin to teach at an art college, probably for family reasons, I would think. And when that had cleared up, she came back again, was welcomed back by Pickering, and put on a new project, which was variable stars. So this was really trying to crack, you know, why are we seeing variable stars? And in particular, those stars where the luminosity of the star seems to go up and down of its own accord. So not eclipsing stars where one's moving in front of another, but literally looking at one star and trying to figure out why is it getting sort of brighter than darker on a regular basis. And she basically catalogued upwards of 2,000 variable stars in the sky. And the key really, to sort of cut a long story short here, she was able to start to identify that there was something special about the variable stars we now call the Cepheids, from the first star of its type in the constellation Cephus that we see in our night sky all the time in the Northern Hemisphere. And the key to that for her was what she realized about the large and small Magellanic Clouds in the southern sky. So there we've got the picture of the large on the left and the small on the right of the Magellanic Clouds. And by looking at the various Cepheid variables that she saw in the small Magellanic Cloud, maybe, and there weren't a huge number of them. She only found probably about 15, 18, something like that. But she was able to start to realize that when she sort of went back over old photographic plates, and this would be very laborious work because she'd have to try and piece together the period, the cycle for a given star by sort of going through various photographic plates and trying to pick the story together, probably over several years. And she began to realize that not only were the Cepheids they had a very sort of regular beat, if you like, and here we can see at the top, in the top graph here, you can see this sort of regular pattern of delta Cephei, the sort of the archetypal Cepheid variable. Every 5.4 days, you've got this cycling, okay? And she realized that what was happening here was that for Cepheid variables that had longer periods, possibly over days or even weeks, the average absolute brightness, or the brightness she could see, was higher. And you can see that graph underneath, you can see this direct relationship between luminosity and the period. This is a log-log plot, it's not a linear plot, but never mind, that's an incredible correlation there. Now, the one thing you might say is, okay, that's fine, but what did she do about distance? Well, she figured out very early on that if she was looking at a nebula here, remember, she wouldn't know that the Magellanic Cloud was a galaxy outside our own. She just saw it as a bunch of stuff with stars in it. And she said, well, maybe that bunch of stuff, all those stars are roughly the same distance from us because they look like they're very close together. Now, of course, we know today that she was right. So she hadn't calibrated the curve, but she was right in saying that she could take distance out of this equation. And for a while, it sort of lay there, and she wrote all this up. And it was obvious that something was happening here. There was something big here that someone needed to work with. And she did write, it's worthy of notice that the brighter variables have longer periods, which may be of some use. This is one of the biggest understatements in astronomy. We now know that as Leavitt's law. It's an unofficial title. I don't believe it's ever been fully accredited to her, but it should be. But most astronomers call it that. So that's really this idea that you can see luminosity versus period. Now, why is that important? Well, if you can calibrate that curve and you can see a very distant star a long, long way away in what we now know would be a different galaxy, and you can work out its period, say somewhere out here, then you automatically know its luminosity. And that's its absolute luminosity. By looking at the star, you know its sort of apparent luminosity, and from that you can work out how far away it is. So this was a massive breakthrough. She'd come here into trying to understand how big is our universe and what do we even mean by that. Of course, the glory had to wait until Edwin Hubble came along in the 1920s, because of course he was fortunate enough to be using the 100-inch telescope at Mount Wilson. And that enabled him to really put the full picture together. We see a picture of Edwin Hubble, or a sort of a painting of Edwin Hubble on the right there. And he basically looked at Cepheid variables initially in the Andromeda Galaxy, which is what we can see down here. And he realized from looking at that and putting the work that Henrietta Leavitt had done to use, that he could work out from looking at the period of these stars, because by then the curve had been calibrated with nearby Cepheids. You realize there's no way this nebula can be inside our galaxy. It's got to be way outside our galaxy. He actually made an error in the sense that he hadn't appreciated there were two different types of Cepheid variables, which meant he underestimated the distance to the galaxy by a factor of about 2 to 2.5. But it didn't really matter. The point was made. Stars exist in other galaxies, and some nebulae were galaxies. So this was really the breakthrough based on Henrietta Leavitt's work. What are the 500,000? About 500,000 glass slides were made during the period that I've been talking about. And they've now all been digitized pretty much. I say 2015, 25% complete. I think I need to update that actually. Pretty much they're all now available. You could look at them yourself anytime. Virtually all the glass slides are now available online. So who do we remember? Well, there is an ending to this story. In 1925, a distinguished representative of the Royal Swedish Academy of Sciences, and that's them what hands out the Nobel Prizes, gets in touch with Harlow Shapley that the Nobel Committee may look very favorably on Henrietta Leavitt for the Nobel Prize for Physics 1926. There's just one slight problem. He was unaware that unfortunately she had passed away in 1921, and of course there are no posthumous Nobel Prizes. But amazing to think that had Henrietta lived another 5 years, she had died of cancer in 1921, she would have predated the first Nobel Prize for astronomy by about 50 years, and a woman to the boot. There you go. None of the people mentioned, male or female, were Nobel Prize winners, despite the work they did. And of course, the reason is because so much work at that time was being done in physics, nuclear physics, quantum physics, etc., etc., etc. There was no way that then, it wasn't, of course, until the 1970s that a Nobel Prize was awarded for astronomy. There have been many more since, of course. If you want to read any more about this, by the way, David Sobel, American author, has a fabulous book called The Glass Universe. Interestingly, when I first wrote all this up, I had not appreciated the book was there. I wrote all this up before 2015 and then discovered that it was all in a book. So I did all the research and then realized that I could now check it because David Sobel had done it for me. So it was very useful for me to check what I'd already done. But it is a fabulous read. She is a superb author. Okay, thank you very much.
Well done, Neville. Can you hear me? This is Paul.
Yes, I can. Yes, absolutely. Yeah.
Right. We have no questions in the Q&A at the moment, but I do have one just to get you started.
Okay.
And that's from me. In the days you describe, it was felt to a degree that women were not as capable as men for scientific work. Take Celia Payne as the example. To what degree do you think that persists today?
Oh, that's an interesting question. Well, I suppose I tend to look at that more from a historic and, you know, sort of bringing that more up to date from a scientific point of view, to be honest. So I won't give you a political answer, but I think it exists today. Well, if you look at the stats, though, I mean, the number of women in sort of higher education in universities around the world, lecturing, etc., is very high. So it's not the same situation. Yes, I'm sure the problem still does exist, and there are far fewer women winning Nobel Prizes, which maybe is also a bit of a giveaway. But no, I mean, there's no doubt that things change from the start of the period I was talking about till the end of that period. Things had changed quite a lot, and I think Pickering takes a lot of credit for that, to be honest. Are there still problems today? Well, clearly there are, but I think they're different problems. You know, I think it's getting there, but certainly I know from working at a university for several years, you know, there were more women lecturers than there were men actually at that point.
I'm a bit biased because I have a daughter who's a lecturer at Edinburgh University, so
all right.
I've got to be terribly careful what I say. She might be watching this. Now, there are still no questions on the Q&A. Oh, hold on. Okay. One has appeared, and it's from Martin. Do you know who worked out the absolute brightness of Cepheus? Was it Hubble?
No, I don't think it was. I'm not sure exactly who it was, but I didn't really go into that because it would have sort of diverted and I would have massively overrun basically. But yeah, so there was another piece of work required, which was, so on that graph, you've got to find Cepheid variables that are closer to us basically, that the distance can be gauged by parallax basically. So you've got to be looking at something that's sort of, you know, no more than, you know, 200, 300 light years away, basically. And that work, a lot of that work was done at the Mount Wilson Observatory. Whether Hubble would have been aware of it, I'm not aware Hubble was actually involved in it actually, because I think it's unlikely, to be honest, because Hubble had a bit of a reputation as a bit of a how can one put this? He liked to be involved in what he was involved in, but he didn't like doing the little work, if you know what I mean. he wanted he really did want the limelight, and so he would have passed that off to someone else, I think. And there would have been many people working at the Harvard College Observer, sorry, not the Harvard, at the Mount Wilson at the time. I think Walter Baade may well have been involved in it, actually, because he's the guy who ultimately worked out that there were two types of Cepheid variables. I have a whole new talk on that, by the way, which I've just finished. But yes, it may have been Walter Baade.
I think from my knowledge that you're quite right about the use of parallax to set a baseline, if you like, to establish the nearby stars and work from there.
Absolutely.
I've got another question for you from our Steve Ashbolt. What started your interest in this period and area of astronomy?
Ah, good question. Well, I guess what really started that off? I think I've always had an interest in the sort of birth of what we would call modern physics, I suppose, really. So right from when I was at school, virtually, school physics, I was fascinated by, the looking back at, who found the first neutron, who Rutherford and the proton, and J.J. Thomson electron, etc. And I was interested in all that, and that kind of, just reading about that sort of, I suppose, as time went by and I got older, and I started to see the links into astronomy, and particularly the links into the birth of astrophysics, which is, by its very title, it's physics in the sky, if you like, and or physics in the stars. And I guess it's really that got me into it. I find it fascinating to read back, just some of the histories of some of the people and what they've done, and what the equipment that they used was incredibly basic. I mean, to get these 500,000 glass plates and to be able to use them sensibly to come up with really groundbreaking science is quite remarkable, to be honest. Quite remarkable. So it's it was born many years ago, I think, but certainly I continue to research these things, mainly through Aberdeen University's library. They have a very good library of astronomy. They used to teach astronomy, but they don't anymore. But they have a very good library of books there, and I'm able to get access to it.
A comment as much as a question from Eric. A lot of what was achieved by these ladies would not have been possible without the astrophotography side of things.
Right.
Do you have a comment on that?
Yeah, in fact, some of them were involved in the astrophotography, but I haven't really got time to go into all that. But Annie Cannon actually travelled to Arequipa and to Mount Wilson, and she was involved at times in setting up the telescopes and taking more photographs and understanding what was going on. But I think where the sort of people power was really acquired at this time was in the analysis. It wasn't in taking the plates. You didn't need a lot of people to take these plates. Once you'd set the telescopes up and you knew how to operate them, it was just sliding a plate in, tracking the telescope manually, and then taking the plate back out again and checking it was done. So that wasn't the difficult bit particularly. We might see it difficult today, but having got to go-to systems, etc. But for them, that was relatively easy. The difficult bit was really figuring out what was going on. It was the detective bit, and that's where the effort was needed, and that's why, virtually all these women were involved in that. They weren't so much involved in actually taking the pictures. That wasn't the bit. That wasn't what Pickering needed them for. That's the main reason.
Don't tell Eric that taking the photographs was easy, because he's one of our noted photographers.
Well, I didn't say it was easy. I said it was. I'll turn it the other way around. What I'm getting at is the detective work was the key to understanding star. Why does star spectra tell you what's going on? That's the link into it. Yeah.
One final question then before we close this session.
Okay.
Is from Darren Moody. Were there any prominent or undiscovered female astronomers working in the United Kingdom at the time of the story?
There were. The most famous is William, the wife of William Huggins. William Huggins was a contemporary of Pickering, and he was working. He had his own observatory actually at Dollis Hill in North London, and he would have been one of the most famous astronomers in the UK at that time. He was working on stellar spectra, and his wife Margaret, who was much younger than him, she became a very, very accomplished astronomer at that period. But interestingly, it's funny. A funny question. What's interesting about this question is that on a visit to the Royal Observatory Greenwich, Annie Cannon, who she travelled quite extensively with her work because people wanted to meet her. They wanted to hear Annie Cannon. Things had moved on from Mina Fleming's day. And when she went to the Royal Observatory, she was astounded to find there were no female computers there. There was nobody doing this work. You know, I said, where is everybody? You know, and they said, well, we don't have anybody doing it. And he said, oh, right, okay. And then that's when she realized that what they were doing at Harvard College Observatory and the mass of work that was being done was pretty much unique. I mean, obviously, it was followed up later on with other women coming into it, but
indeed,
very
good, very good, Neville. I'm going to hand back to Eric then for the next word.
Thank you. Thanks very much.
I would just like to take this opportunity to thank Neville for a most interesting and inspiring talk. Absolutely fascinating. If you scroll through some of the comments in the chat, you'll see how much it was appreciated by the audience. Now, normally, Neville, you would be receiving a token of our appreciation and a thank you card designed and printed by Pauline now. But just to let you know, you will still receive these things, except that they'll be sent to you by email. So Neville,
well, no,
very much once again.
I will need your address, please.
I'll send you my address, Pauline.
That'd be great. Thank you.
Yeah.
So now we're going to move on to one of my favourite bits of our monthly meetings, the Club News AstroPicks targets for the month. And this is going to be very ably presented by our very own Pauline McRae. Pauline, over to you.
Okay. Right, so what I'm going to do is to talk about noctilucent clouds this month instead of doing a constellation. And this is simply because you will all have noticed that the skies are really light at this time of year. So light that we just do not get to see very many stars, apart from the brightest ones, of course. And summer months are a really good time to go noctilucent cloud hunting. Now, noctilucent means night shining, and they really do seem to shine against the twilight sky. And this is illustrated really quite nicely from with this photograph by Dave Davidson, which was taken just a few days ago, the Saturday night into Sunday morning. And this seems to have been the start of the noctilucent clouds up with us in the north of Scotland. They are often this wonderful electric blue colour, which merges into a brilliant white, almost silvery white, but incredibly bright down on at the base of the blue. And they can form fine swathes of delicate filaments. Sometimes you get wave patterns, sometimes it's just these really fine tendrils. But you tend to get structure, and this is what makes these clouds look so exquisitely beautiful. They might cover quite a bit of the sky, or you might just see them in just one small part of the sky. But you usually notice them in the northeast early on in the night, And then very slowly, they move across to the northwest as the night goes on. So by the end of the night, they are usually in the northwest part of the sky. And you'll also notice that there appears to be this perpetual sunset merging into the sunrise all the way along the northern horizon. And then just above this beautiful vista is where you find noctilucent clouds. Now, they're visible from maybe third week in May to around the first week in August, but this does vary a little bit. And this year, NASA's AIM satellite found the first noctilucent clouds on the 17th of May, and that is really early. We can see them perhaps best between 11 in the evening to maybe 2 in the morning, but of course they are seen outside these times as long as it's dark enough. And of course 11 o'clock tonight, for instance, would be too light to see them. But 1 o'clock in the morning seems to be a really good time for seeing noctilucent clouds. They can be viewed from a narrow latitudinal band from around 50 degrees to maybe 65 degrees north, and of course south, because they can be seen in the southern hemisphere during their summer. Britain is right within this band, and of course the north of Scotland is bang in the middle, so we should be treated to some really good views. But this 50-degree latitude is not fixed in stone. Noctilucent clouds are seen much further south than they ever used to be. And in fact, last year they were seen all the way down in California. And this might have something to do with climate change. They are illuminated by the sun when the sun is below the horizon, between about 6 and 16 degrees. Now, if the sun is further than 16 degrees below the horizon, it'll be too dark, you're not going to see anything. If the sun is less than 6 degrees below the horizon, it's going to be too light and you won't see anything. So, but 6 and 16, these are approximate numbers. And if you think about it, if these clouds can be illuminated by the sun when it's below the horizon, that would suggest that they are very high up in the atmosphere, and indeed they are. They're found in the mesosphere, about 80–85 kilometers high, and they can be considered to be our highest clouds, whereas our weather clouds are found right down here in the troposphere. They're formed from tiny ice crystals that surround even tinier particles of space dust, which has been shed by micrometeors. So you can think of noctilucent clouds when you look at them as little crystallized bits of space dust. But these ice crystals can only form when the mesosphere is minus 120 degrees centigrade or colder. And that only happens in the summertime, which is why we don't see noctilucents all year round. Now, these ice crystals have just a perfect size for being able to reflect the sunlight in such a way that it makes the clouds look blue. But there's also some absorption of ozone as the sunlight goes through and reflects off these clouds. And that, of course, also makes them blue. Now, we have a lovely photograph from Sue Shackleton of North Ronaldsay Astronomy Group. And this is quite beautiful. It's quite ethereal. You've got these wonderful strands of this whitish appearance from the noctilucent clouds. And this, of course, being up in Orkney, look at the light compared with the photograph you saw taken by Dave, because Sue took hers on the same night that Dave took his. Sometimes noctilucent clouds are obvious. Now, I took this one in 2014 I have seen them since that time, but I use it because this was such an amazing display. You've got the blue merging into this really bright white. You have these wavelets within the noctilucent clouds, and you've got fine strands, these fine tendrils. And then you can notice that there are these really dark, dirty, dark smudges. And these, of course, are the tropospheric clouds, our weather clouds. The fact that they're in front of the noctilucents means that they are lower than the noctilucent clouds. Sometimes they're a little bit more subtle and you have to look a bit more carefully. And this was a photograph by Eric a couple of years ago. But you can see you've got these fine strands of this whitish cloud merging into this structure that you can see down here. You've got the dark weather clouds, you've got this strand of weather cloud across. But I think these are also weather clouds, but Eric might want to disagree with that. And sometimes it can be difficult to tell if you're looking at noctilucents. Usually they'll have some form of structure within them. They should appear this bluey color, maybe merging into this bright white color. And you've got to also make sure that you're looking north, because if you're not looking north, then the clouds you're seeing will not be noctilucents, unless you're in the southern hemisphere. But it's when you get pictures like this and you think, not really sure, but they are this whitish color. Now this, incidentally, is a picture or photograph taken in the southern hemisphere, and their noctilucents are not a patch on our noctilucents, so we are incredibly lucky to live where we do. Okay, so you've got a nice clear evening and it looks like it's going to be clear overnight. So do you stay up until 1 or 2 o'clock in the morning to see whether noctilucents will appear? Well, you could do. I mean, the sky in the summertime is absolutely beautiful anyway. But if you would want to go to bed and have sleep, then the thing to do is to drink a cup of tea, and then you have to get up at 1 o'clock in the morning. And this is the way I manage to see most of my noctilucents. But the other thing you can do is to go onto spaceweather.com. This is a great site that I use for looking to see whether the aurora is visible. But with this screenshot taken a few days ago, they're talking about the noctilucents. They're actually saying that, yes, it was May the 17th that they discovered the first noctilucent clouds of this year. So what you do is to scroll down. We've got a nice picture here of noctilucent clouds. Keep strolling until you come to this little box here labeled noctilucent clouds. Click on that, and this is a picture of where the noctilucent clouds are found over the polar region. So that's the North Pole. If you look down here, this is the line, well, this is a 0 longitude line which goes through London. So there is Scotland. And if these clouds are nearby, or even over the top, which is even better, then you can be fairly sure that you should get a good display of noctilucent clouds. So happy hunting. Now, I'm just going to try and get through this quite quickly because there are a number of photographs. And as Eric has already explained, we're holding our monthly meetings by Zoom using the Zoom platform that Sigma have. And it's a really big thank you to Sigma. Now we are contributing to this. So this is where your membership fees are going. And as Eric pointed out, we have 3 more meetings definitely confirmed. And the other thing Eric said, of course, is that he's hoping, some of us will also, are hoping to show live images of the sun, moon, and perhaps other observing phenomena. And maybe with his new gear, which consists of a Lunt telescope. So the Lunt is like the Lunt that we have at the observatory. It enables you to see the chromosphere, which is the lower atmosphere of the sun, and it gives us this gorgeous color. Very little going on the sun at the moment, but you can just see these prominences at the side. However, yesterday, Eric took this photograph. Wonderful prominence, more prominences here. This is a really splendid photograph, and he's only just getting to grips with the processing as well as taking the pictures with his new toy. Right, and then back in March, Eric again was busy in his observatory photographing the Sol Nebula in Cassiopeia. It consists of gas and dust, and it's making new stars, many of which are these big, bright, blue, luminous stars, which produce copious amounts of radiation and stellar winds. And they're actually sculpting these amazing pillars that you can see just here, and Eric's managed to capture them. And then if you look at the picture as a whole, it's just incredible. It's a beautiful image. Eric also managed to capture a supernova within this very faint dwarf galaxy in Leo. But look how bright the supernova is. It's extraordinary. It was seen on April the 21st. This is a type 1a supernova. It's where you have a white dwarf drawing in material from its companion. It takes too much, goes over its limit, which this sets off a thermonuclear explosion, and the entire white dwarf is obliterated. And these supernovae tend to be really bright. And then we have the wonderful moon pictures from Dave, where they are just crisp and clear. And he doesn't use a telescope. This is his camera and a telephoto lens. And they're beautiful. He even managed to find Comet Atlas. And remember, without a telescope, this was a remarkable feat. I love this one. This is Venus next to the Pleiades. And then this is the moon with the crater Tycho by Karen McIntosh. She used her telescope, and it's always difficult when you're looking at the moon through a telescope because it's so bright, it tends to bubble and boil. So she's done a really good job. Not to be outdone, I've got one in this time. This is of the sun taken through my ETX125 with a solar filter. Every time I managed to get the entire sun in the eyepiece, it was a rubbish photograph. The best photos were the ones with half of it cut off, because at that point the sun just simply moved out of the eyepiece. But it was with a mobile phone, so I was really pleased with the result. And your challenge for the summer is really what we had last year, and it works best because there isn't a great deal to look at. So we've got noctilucent clouds already. Dave and Sue have got their images in, or the moon, and of course we've got Karen and Dave with their images so far. So let's see what the rest of you can do. Now, this is not a wonderful photograph. This is noctilucent clouds taken with my mobile phone, which unfortunately no longer seems to be able to focus in on the sky, which is why they tend to be a bit blurred. And these, not quite as good, not quite as bright, and these were noticed on the Sunday into the Monday morning, Sunday night into Monday morning. But if you have a camera on your mobile phone, you too can take a photograph of noctilucent clouds. So come on, let's see your photographs, send them off to Eric, and then he'll send them to me and I can put them on to this the next time. Now, a little bit of sky stuff, most of which probably won't be much use, but Venus has disappeared. As you will have seen, it's no longer shining brightly in the west. It'll re-emerge in the morning sky. And then on the 19th of June at 8:39, there's going to be a daytime occultation of Venus with the waning crescent moon. So it's going to be in the east for quite early on in the morning. The crescent moon could be quite thin, maybe it's going to be fairly difficult to find. But Venus, you can see quite easily during the daytime if you've got a guide, and the moon works well for that guide. But if you're going to use binoculars or a telescope to look for it, for goodness sake, be careful, because the sun will not be far away. Now, another planet that we should be able to see at this time of year, but because of the night sky being so bright, it's unlikely. But Mercury is at its furthest point from the sun in a couple of days' time. Should be easy to see, but not with the light skies. And I have searched and searched, and even with binoculars, I can't see it. I can't see Capella at that time either, so I'm pretty sure we're not going to see Mercury. But if you do see Mercury, please let me know. Jupiter, Saturn, and Mars can be seen after midnight. Jupiter, nice and bright, easy to find. Saturn is close by, so if you see Jupiter, you can see Saturn. Mars rises about an hour later, and it's reasonably bright, so with any luck, you'll be able to find that too. Now, this last one I have simply included because somebody might say to you, oh, there's an eclipse of the moon on the 5th of June, but it's a penumbral eclipse. And there's never really that much of a noticeable difference in brightness and color, so it's not worth always looking for. And it's only going to last 9 minutes anyway. So I don't think you'll get to see much with that. 2 weeks after an eclipse of the moon, you get a solar eclipse. This time it's an annular eclipse, but of course it's not visible from the UK. But if you see photographs of it, I think it's going to be visible over Asia. If you see photographs, you should get a really beautiful, quite a spectacular view. And I'm going to now hand back to Eric.
Absolutely fantastic.
Do I have to stop sharing?
I'm not sure.
Oh, stop share. Yes, there we go. That's it. We'll get it right.
Absolutely fantastic, Pauline. What a lot of work you have put into that. I'll tell you one thing. I know one person who's going to be trying to get that occultation with a thin waning crescent moon. That'll be Dave.
Dave, yeah. I thought it would be too. Yes.
So I'm looking forward to seeing something from Dave there anyway. So, great. Thank you very much for that. Now, I've got a little section left for questions and answers from our members about the club or anything at all, presentations of the club. Perhaps if there's anything folk want to ask me, come in with chat or questions and answers, and we'll try our best.
Nothing on the Q&A yet, but I think that perhaps what we could ask members to do is to give us a bit of feedback as to how they found this evening. By email would do just fine. Because the way that the coronavirus thing is at the moment, we're going to be doing, I would imagine, at least 2 more of our meetings in this format. And anything we can do to improve has got to be a good thing.
Yeah, I agree that, Paul. This is all very new to us, so we've probably had a few little glitches along the way, so we need to be told. Although I've enjoyed it, I have to say. It's been fantastic.
Yeah. No more questions, Eric. I suggest we wrap up there. We're on about the right time.
That's great. Thank you very much, everyone, for attending. I counted 35 Zoom attendees, so there's possibly more if there's more than one person at a screen. So I think that's a rather good attendance for our very first Zoom webinar. So thank you, everyone, for attending. We will let you know if and when we're going to be doing live observing or tutorial sessions. We're definitely going to be encouraged by this. So thank you. Stay safe.